Okay, I think we're ready. Hi, everyone. I guess small crowd today because people are staying home preparing for the midterm or something. So that's reminder number one, is that you have a midterm tomorrow. And again, remember to check what room you're supposed to be going to online, because people go to different places based on their last names. For those of you who didn't see on Piazza, we have a review session happening today that Fahad is going to be leading. That's going to run from 4 p.m. to 6 p.m., so right after this class is out, in the HP auditorium in Soda, right? Yes. Okay, so the big auditorium in Soda. Go there if you want to do some prep. And as a consequence, Davis's office hours are going to be pushed back today to allow people to go to both those and the review session. And also my office hours are going to get cut a little bit short tomorrow so that we can go set up the exam rooms for you to get there. Any admin questions before we start? Okay, cool. So what we're starting today is the kind of third major unit in this course. So we talked about how to do to solve search problems of various kinds and how to learn in the reinforcement learning setting, the MDP setting. Then we spent a lot of time talking about how to do inference and more structured probabilistic models. And the last unit we're going to be talking about in the course, so starting today and going on really up until the final, is going to be on learning. So, we spent a lot of time talking about how to figure out the answers to our probability queries if we already know how these probabilistic models are specified. And so the last question that we need to answer is how those models actually do get specified in the first place. So to put this another way, we've been looking at how to use models to do optimal decision making, and the machine learning portion of this course is going to be all about how to produce models that we can use in the ways that we've been talking about before. When we talk about learning models, we generally mean one of two things. Either for fixed model classes, say a fixed Bayes-net structure, how do we figure out what probabilities, what numbers to plug into that Bayes-net structure to give us a sort of fully specified Bayes-net? The other thing that people talk about when they talk about machine learning is figuring out how to actually acquire these structures in the first place. And that's a little beyond the scope of what we're going to talk about in this class. I think it's just also as a machine learning problem, a lot less well understood. And so what we're going to be focusing on here and for the rest of the lectures in this class are this first question of how do we learn probabilities, or how, more generally, if I know the structure of my model but not the parameters for it, how do I learn those parameters? And so specifically what we're going to be looking at today is a particular class of machine learning model called Naïve Bayes, which, as the name suggests, is going to be based on a Bayes-net and based on doing inference in Bayes-nets, but that's going to make a sort of particular set of very general independence assumptions that's going to allow us to apply it to a variety of different tasks. So let's start by motivating the problem that we're actually trying to solve here. And the problem that we're trying to solve is what's called classification. And so in classification, basically, I have an input, which might be some kind of thing generically, and I'm trying to produce an output, which is always going to be some kind of discrete label. So when we talk about classification, we generally mean, problems like, yes or no, is this a spam email? Or, of all the digits between 0 and 9, which digit is it? And not more structured things like what's the sequence that answers this question, or what's the kind of tree-shaped object that answers this question. So again, classification, we're mapping from inputs represented somehow to labels. And the kind of canonical example of this is spam filtering. Do people still get spam? Is this still a thing that happens? Okay, it feels like this technology is good enough that it's still like, it's not as much an issue as it used to be back in the day. And actually, the reason it's not as much of an issue as it used to be back in the day is because of machine learning. So spam looks like this. I get an email, maybe an email saying, "Dear sir, first I must solicit your confidence in this transaction that by virtue of its nature as being utterly confidential and top secret." Do we think this is an email that one of my friends sent to me, or do we think this is a spam email? This is a spam email, right? But how do we know this? We know this because we can look at it and we can see that this email has certain properties that suggest to us that it's a spam email, right? I'm being addressed as "Dear Sir," and nobody ever addresses me as "Dear Sir." They're writing in this kind of like weird, high-blown language that's also not quite proper English, and so on and so forth. So the question is, how can we set this up in such a way that a computer can make these same kinds of decisions? And the way in which we're going to go about this is we're going to learn it from a collection of labeled examples. So we're going to start by collecting a bunch of emails from whatever source we acquire emails from, and we need to label these emails with whether those emails are spam or what we're going to call ham. So emails that are not spam, emails that are real emails that I want to receive. And there are a bunch of different ways in which you can get these different labels when you're starting out. One thing you can do is you can get a bunch of expert email readers whose judgments you trust, and you can have them all sit down and maybe have one of these people label each email, and what you'll wind up with at the end of the day is a collection of emails with labels produced by humans that you trust. Another thing that you can do if you don't have access to trusted email readers is you can just like throw these things up on the internet and pay internet randoms to annotate these emails. And you don't know who these people are, you don't trust them, and so maybe the labels are lower quality. But if you get enough people to annotate, multiple people annotating the same email, you hope that kind of the consensus will be as good or better than you would have been able to get with experts. The last thing that you might be able to do is sort of get people to produce these labels for free. So maybe what I do is I set up some kind of free online email service for people to use, and then I put a little button in that email service where people can mark their emails as spam, and we hope that in exchange for using this free email service that I'm providing to them, they will annotate my data for me for free. Right, and they might do this just because, the button is there and that's how you make the emails go away and this is a useful thing. Or they might do it because they know behind the scenes, we're doing machine learning, and the more labels they provide for us, the less labels they're going to have to do in the future because our spam classification is going to get better and better. So generally, as a kind of engineering thing, when we're starting to do these problems, one of the major bottlenecks is just figuring out where this data is going to come from. But once you do that, then we can start to do the really interesting thing, which is machine learning. Okay, so two things that we need to solve one of these classification problems. The first is a data set of labeled data. The other thing is we need some way of figuring out how to represent all of this data that we've collected in a way that our machine learning model can consume. And so, sort of practically what that means, right, if you remember when we talked about specifying a Bayes net, we would have a bunch of different random variables that would interact with each other in some way. What we're ultimately going to develop is a sort of Bayes net structure for solving these kinds of classification problems, but I need somewhere in this Bayes net that I can plug in a representation of the email. And so what that means in very general terms right now is that I need some way of turning this email here into a list of random variables that I can represent inside of some kind of Bayes net structure. And we're going to call these random variables that we extract from the actual email that we get features. Features can be anything. Feature engineering is something that people spend a lot of time thinking about. And so, as a kind of example of things that we might care about, maybe we're going to look for specific words. So I'm going to have a binary random variable that'll be true if the word free in all caps with an exclamation point appears in this email and will be false otherwise. I might, do the same thing for the word solicit. I might do slightly more general sort of template features that say this thing is going to be true if I see any kind of monetary value appearing in the email and false otherwise, or any kind of word that's in all caps appearing in the email and false otherwise. And then we can even start to do things that look not only at like the text of the email, but the whole context in which it occurs. So who sent this email? Do I recognize this person from my address book? And so on. And one of the key things to take away here, right, if I have a feature, I have a random variable for every word that I might see in an email, then I'm going to have many, many, many random variables, right? I'm going to have as many random variables as there are words in the dictionary or even misspellings of words in the dictionary. So it's going to be especially critical in these cases that we're looking at today to develop Bayes net models that support really fast inference, because the number of variables in these Bayes nets is in general going to be very, very large. So yeah, here's the spam filtering problem, and again, what we want to be able to do is to be able to say, yeah, this first email is spam. The second email, where they're trying to sell me 99 million email addresses for only $99, is probably also spam, and some friend of mine complaining about her computer being broken is maybe not spam. So yeah, questions about the general setup? Yeah. That is a great question. I mean, in general, you kind of use what you know about the structure of the domain. There are, when you're working with text, there's a kind of standard set of text features that it's always good to throw into the bag. When you're working with images, historically there was a kind of standard set of image features that you would throw into the bag. We're going to talk very briefly at the end of this course about ways of starting with sort of really simple, stupid collections of features and having the model automatically invent richer features and feature templates on its own. But, for a lot of practical applications, the easiest thing is just to, make something up. And, you know, the right way to think about that is what, you know, if I didn't get to see the original email and someone just had to, like, give me a list of these binary random variables instead, what are the kinds of things that I would like to see that would be kind of compact and general enough for me to be able to make the right decisions, and still, yeah, be kind of comprehensible. Other questions? Okay, cool. So here's another application that comes up a lot when we look at these kinds of things, is digit recognition. So here, rather than having a collection of words come in, we're going to have some kind of grid of pixels, and maybe this is a black and white image. So, you know, one kind of natural way in which we could, well, we'll talk about features in a minute, but yeah, so the general setup is the same, right? That I'm going to have images. I will have had people annotate each of those images with the actual number that appears in the image, and you know, when I get new images coming along that look like this, I want to be able to predict from scratch what number this is. So this is a 0, this is a 1, this is a 2, this is a 1 again. And this last thing here, kind of who knows, right? Maybe it's a 6, maybe it's a 2, maybe it's a 0. And so one of the things that's going to be really important when we work on these kinds of machine learning tests is developing techniques that are robust to having weird-looking training data where maybe the label is wrong or maybe there's some uncertainty about what the label is supposed to be. So yeah, we were talking about where do features come from. What might be some good features that we could define in this digit recognition task? Keeping in mind that all you're going to get to start with is a grid of pixel values, and maybe these are just going to be kind of like 0, 1, whether this pixel is black or not in the image. Yeah.
Maybe we start with just a basic template of what its automatic perfect number would look like and see how many pixels match up to that.
So what do you mean by the perfect number?
I mean, if you were to type in the computer's automatic font, that's the template.
Okay, so the proposal is I create a sort of template that looks like this, that's like a perfect 2 or maybe a sort of noise around a perfect 2. And then I can compute some value which says, of all the pixels that I saw in the actual image, how many of those pixels sort of line up, overlap with the template that we saw here. Yeah, so that seems like a really good kind of feature template. And assuming people's images mostly overlap with these things, this will probably be a pretty good way of doing this. And so notice we need 10 such features in order to do this, because we want to fire 1 for every class that we might see. One thing where this might run into trouble a little bit is, you know, maybe here's my perfect 1 in the middle of the image, and then the actual picture comes in, and you know my 1's kind of off to the side and it's slanted. So there's actually no overlap here at all, but this is also a 1. What other kinds of features might we want to define here? We're not moving on unless we get at least one more set of image features. Yeah. Okay, so how is that different from the one that we were talking about before? Mm-hmm. Right, so we could measure the number of pixels that are different in the actual image that we got and one of these templates that we've defined ahead of time. What if we don't have templates ahead of time? I just, you know, somebody's told me that this is a 2, but I don't have any way of generating a 2 myself. Yeah.
Remembering it and then matching all the future times you're looking at it.
Okay. That's a good idea. That's really complicated, and we will talk about that much later in the class. But the idea is I remember the label for individual training examples I've seen, and when future things come in, I see how similar they are. So yeah, remember that for like a week and a half, because that'll be important later. Yeah?
Trying to measure geometrical constraints, like is there a loop here? Like where's the loop? Or where's like an intersection of 2 lines?
Okay, cool. Yeah, so rather than defining templates that look at whole whole images like this 2 or this 1 here, we could just say, let's look for little cross shapes, or let's look for little loop shapes, or let's look for little plus shapes, and kind of sweep these templates over the whole image and do things like that. So yeah, that's another natural feature template. One thing that we haven't talked about at all that would be a sort of simple thing to do is just like an indicator variable, a binary variable for every pixel in the image, right? Is this pixel on or is this pixel off? Because maybe there's some information just in the raw pixel values there. Questions about why we've defined the particular set of feature templates that we have for this task. So yeah, and features for images in particular is the kind of thing that like the research community spent 30 years just trying to come up with better and better feature representations for doing these sorts of tasks. But this is generally the right idea. So yeah, we might have indicators on individual pixels. We might have indicators on whole shape patterns, whether those are like canonical versions of our letters or smaller little fragments of things. And I think the main thing to take away here is just that these kinds of classification tasks come up all over the place. They're out there in the wild. You kind of have had them used on you, and you have used them all the time. So like we said, in spam detection and in OCR, when your email comes in, it's getting checked by some kind of spam filter that's been trained. When you put a check in the ATM, or when you put a letter in the mail, the digits on the sort of money field on your check or on the postal code on your letter are being scanned by a computer and are being passed through an OCR system of this kind. Other applications, medical diagnosis is actually kind of an interesting one, because we've been in this state where for certain kinds of diagnosis problems, computers have been better than people for a long time, but the regulatory situation in medicine is so scary that a lot of these systems don't actually get deployed in practice, even though they are better than your doctor. It would be better than your doctor if they were used in practice. Automated essay grading. If any of you are planning to take the GRE sometime soon, maybe to go to graduate school, which you should all do, your GRE essay is actually graded by a computer and then only checked against a single human. And if the human and the computer disagree, they bring a third human or a second human in, but most of the time the computer and the human don't disagree. So we can actually do automated essay grading. Coming soon to CS188. And yeah, again, if you've ever gotten like a phone call from your credit card company asking if you really just bought a boat in Croatia, that's because they have things that look at every transaction that comes in and tries to classify it as fraudulent or not fraudulent. So the point is, this is all over the place, and this is, has for a long time been one of the more robust commercial applications of things that we do in AI. Okay, so hopefully that's enough motivation. Let's now talk about how we actually solve these kinds of classification problems. And so what we're looking at today specifically is what we're going to call model-based classification, which just means what we were talking about before, that we're going to specify some kind of probabilistic model, some kind of Bayes-net ahead of time, and the learning problem that we're trying to solve here is figuring out what the parameters for that Bayes-net should be. So yeah, again, concretely, structure is fixed. And what's going to happen is basically, having picked some kind of Bayes-net structure, and you'll see what structure we pick in a minute, one of these variables is going to correspond to the label that we're trying to assign for our classification task. Let's use a different color. And all of these other things are going to be feature values. And what I ultimately want to predict is the distribution over the label given the distribution over the feature values. And so, the sort of thing that we have to learn is what all of the conditional probability tables that define this Bayes-net are. And the thing that we have to decide ahead of time before we even start trying to learn is what structure that Bayes-net should have. So here's the Bayes-net, and this is what's called a naive Bayes model. So whenever you hear the words naive Bayes, you should think of this structure here. And the main thing to notice with this Bayes-net structure is that we have our label, which we've called Y, and all of the arrows in the Bayes-net come out from that label Y. So what is the conditional independence assumption that this model makes? Yeah?
Assumes the features are independent of each other if we have one.
Okay, that's exactly right. So given the label, all of the features become totally independent of each other. We're going to see in a minute why this leads us to call it a naive Bayes model. So, again, coming back to this digit recognition example, we might have, so our Ys are going to be the actual digits we're trying to predict, and then we've defined each of these features, which are template overlaps or, individual pixel intensities for particular places in the image. And we're going to treat each of these things as being conditionally independent given the label. So what are the quantities that we need to represent? Well, we need our P of y up here, and then for each f sub I, we need P of f sub I given y. And these two things together are going to fully specify this model. Why do we call this a naive model? Well, think about our image example. Suppose I've started filling in pixels in this image, and I tell you also that this is a depiction of a 1. And I ask you, what's the probability that this pixel is going to be on or off? Under your kind of normal model of what this image should look like, what's the probability that this red pixel should be on? Very low, right? Because we've kind of seen that this person is drawing the 1 over on this side of the page, and so, you know, this should be off because we don't expect to see any ink there. The point is, in a naive Bayes model, knowing that this is a 1 says that basically I shouldn't actually, I should kind of ignore the fact that these things are here at all, and just like, if ever I see pictures of 1s in which this square is filled in, then I should assign some probability to this square over here. Yeah, and so this is why we call it a naive Bayes model, because it makes an incredibly strong independence assumption among all of the different features that you've defined for your problem, in this case, the pixels in the image. Questions about what's going on there? Yeah?
So, are you saying that the naive Bayes model would assume that the red and the blue are dependent, or?
Yeah, given the label. So to put this more concretely, suppose there were only two kinds of 1s. Suppose there were 1s that appear on the left side of the image, and there were 1s that appear on the right side of the image. What a naive Bayes model says is that if I tell you that this is a picture of a 1, and I start filling in probabilities, really this is going to be like a coin flip for each of these things on each side of the image. So if I sample from this model, and I look at what that sample looks like, it's going to be like half of a left one and half of a right one, because all of those individual pixel values are made independent by the particular label that I'm trying to assign. Do people understand this? This is an important thing. Shaking some heads still. Okay, so let's do this more concretely. Let's suppose that there were only 4 pixels in the image. Let's try this. Okay? So I can either get 1s that look like this, or I can get 1s that look like this. Okay. Now this is a joint distribution over all 4 pixel values, right? That puts 50% of its mass on this configuration and 50% of its mass on this configuration. So, can I represent this joint distribution using a Bayes net with this structure that we have up here? Hands for yes. Hands for no. And a lot of people are uncertain. Okay. Think about this, because these kinds of questions are going to be important on the midterm tomorrow also. You cannot represent this joint distribution using what we have up here. If these are the two ways of sort of realizing a 1, you can't do this. Why can't you do this? Because, right, I have a Bayes net that looks like, I need more drawing space. But basically I have a Bayes net that looks like this thing here, but with 4 variables, right? And each of these 4 variables depends only on the label that I've assigned. So if I tell you y is a 1, then all I can say is, what's the probability that this square, with the green box around it, what's the probability that this square is on or off, given that we've seen a 1? What's the probability that this square is on or off, given that we've seen a 1? And there's no way for me to couple those two things together, right? Because they are conditionally independent, given the label that we've already seen. So a random sample from this particular Bayes net that we've defined for our 4 pixel image task is just going to fill in each of these squares uniformly at random, because in 50% of the, 50% of the time when I've seen an image, this square was on and 50% it was off. 50% on, 50% off. Is this more clear now? Okay, cool. So this is an important kind of high-level principle. What we have written down, this Bayes net, is a terrible generative model for actual images. If you sample from this Bayes net, they will not look like digits at all. But it might still be a good predictive model. So we can have things where if you sample from them, they look bad, but they still give us good performance in practice. And we're going to see examples of this in a minute. Okay, so to kind of, formalize this again, what we've written down here is a general naive Bayes model, and a general naive Bayes model looks like this with arrows pointing outward from the label. And what does it take to represent this? Well, ultimately what we're going to be encoding is some kind of joint distribution over labels and all of the feature values. There are exponentially many such things because, in principle, we could see all feature values in all combinations. But because of the particular Bayes net structure we've written down, and because of the independence assumptions that are encoded in this Bayes net, we actually have a much more compact representation of that, right? So how many numbers does it take for me to specify P of y? Say for the digit task. How many different values can y take on? 10, right? So, and more generally like this, which here is going to be 10. Okay, how many numbers do I need to specify each of these things for a binary valued feature? Okay, so a single term in this product. Feature can take on 2 values. Y can take on 10 values. So just 2 times 10, right? 1 for every combination there. And so to include the whole product, this is going to be n times 2 times 10, right? Or sort of more generally, erase this. N features times the number of values each feature can take on times the number of labels. So what we've ultimately wound up with here, and this is really crucial, is a model that only requires a number of parameters linear in the number of features to specify it. Why didn't we just try to model the whole joint distribution? We saw in the previous slide that modeling the joint distribution is going to give us more expressive power. We could actually capture the fact that ones either look like this or like this, but nothing in between. So why didn't we try to model the joint? Yeah.
Would the joint be too much? I mean, looking at that, the one on the left side of the joint.
Yeah.
And then I feel like that takes a lot more
A lot more what?
storage space.
Yeah, a lot more numbers. So it's not just a matter of how much space is it going to take us to write down, but also like how much data do we actually need to figure out these parameters. It's going to be not universally, but mostly true that the more parameters that your model has, the more of these numbers you have to fill in tables, the more data you need to actually learn a good version of that model. So there's a kind of fundamental trade-off between statistical efficiency and the expressive power of your model. So the more complicated the distributions are that you can represent, the more data you're going to need to learn to represent those distributions. And so this naive Bayes model that we're talking about today goes kind of all the way in one direction there and says we're going to make basically every independence assumption that it's possible to make, and that's going to allow us to have a really compact model that is easy to learn. Okay. So what does the inference problem look like here? This is hopefully something that's totally familiar to you guys because you know how to do inference in a Bayes net that looks like this. And remember, what we're trying to compute, sort of generically, is the joint probability of all of the different values that y might take on for fixed values of these features. So our kind of testing scenario looks like this, where we don't observe the guy on the top. We do observe everything on the bottom, and we're trying to figure out what's happening on top. And so we just form the joint distribution using our Bayes net. I've written on top of this image, but you guys know what's underneath it, right? We can write down that joint distribution in terms of quantities that the Bayes net defines. We just compute each of these things, we normalize, and what we get out at the end is P of y given all of our feature observations, which is a distribution of labels given the evidence that we have. Questions about this? This is not new. Okay, good. So what do we need to actually apply this naive Bayes thing in practice? Well, we need the inference technique, which is what we just saw, which is given that I've already learned all of the parameters for this model, how do I actually figure out my distribution over labels? But the other part, and the part that is really about machine learning, the part that we're talking about today, is learning these local conditional probability tables, is learning what P of y looks like, and learning what each of these P of f sub I given y looks like. In general, sort of when we're talking about machine learning models, generically, not even just Bayes nets, but other classes of models as well, we refer to these numbers that we're trying to learn, in this case the parameters that we're trying to fill in, as parameters. I've been doing this some in this lecture already, and the sort of standard notation for these things, the Greek letter that you use when you're writing down a set of parameters, is you use theta. As a warning, my lowercase theta looks like this, so just be aware that when I write that, that is also a theta. Yeah, and so the thing that we're trying to figure out today is where these conditional probability tables actually come from. Now, you guys have actually already seen an example of this in 188 already. Who remembers where? Yeah, in the back. Okay, in prior sampling, are there parameters that we're trying to learn? Yeah, so the question is, where have we estimated numbers to put into a table of probabilities based on observations of the world that we've seen? This side of the room. This side of the room has been very quiet today. Think back to MDPs. What came after MDPs? Sorry? Q-learning. Okay, what came before Q-learning? Reinforcement learning. What kind of reinforcement learning? You guys are close enough. Model-based reinforcement learning. Remember when we were doing model-based reinforcement learning, we said, you know, I have this like transition function SA S prime. This is a bunch of probability tables, and how am I going to learn the values for this transition function? I'm going to sort of look at all of the transitions that have actually happened to me in the world. When I was in state S and I took action A, where did I wind up? And we filled in the tables associated with this transition function just by counting the number of outcomes that we actually saw when we were kind of interacting with the world in practice, and then normalize those to get probabilities. So what we're doing here in this sort of first pass at parameter estimation is basically the same thing. So where do parameters come from? Well, you can ask humans to write them down by hand, but humans are really bad at this and we don't want to do this. And so what instead we're going to do is use training data, and in particular, the sort of natural thing to do is to look at the empirical rate at which outcomes occur. So if I, you know, have a single Bayes net, or a Bayes net over a single variable of color, and I want to figure out from samples that I'm getting of the world what P of C is, well, I have 3 samples, 2 of them are red, 1 of them is blue. So let's just count the number of times each outcome occurs and normalize by the total of samples. And we say here that the probability of red is 2/3, and the probability of blue, is 1/3. Sorry. Okay, so is it clear what we're doing here? Yeah. So the point is just, this is structurally, so, right, when we were doing model-based RL, we said there's some kind of transition function, and I want to learn the parameters of that transition function. And the way I'm going to, right, this looks like if I'm in S and A, and I'm going to wind up in S prime. So this is like when, you know, S was state 1, and I took action 3, let's say I took the action go left, then, you know, and I wound up in state 2, 0.2 fraction of the time. When I was in state 1 and I took the action left, I wound up in state 3, 0.8 of the time. When I was in state 2 and I took the action right, I wound up in state 1, 0.7 of the time, whatever. Do you remember that? So the thing that we were doing there, where we were just like looking at samples we had of the world, counting them up, and then normalizing them to fill in a table whose values we didn't know ahead of time. That's the same kind of learning that we're doing here. And that's distinct, for example, from sampling, the sampling techniques we were talking about before, where we know the table ahead of time and we're just trying to sort of compute some other quantity that we could get explicitly. Here we don't have anything to start with but our samples, which are, you know, sort of things that happen in the world rather than things that we constructed ourselves. Yeah, so questions about this. And we're going to see at the end of this lecture why we call this quantity P sub ML. Right, so in a Bayes net in particular, just to make this concrete, I wish there were a way of obliterating all of this. I'm just going to use this as scratch space for a minute. To make this concrete, like if I have my Bayes net, I have two features. How am I going to estimate, this is y, this is f1, this is f2. How am I going to estimate y? It's just the fraction of, you know, P of y is just the fraction of things that wind up with one label or the fraction of things that wind up with the other label. P of f1 given y1 is going to be maybe a 4x4 table, which for each value of y that I saw in the training set was f1 on or off for that y. So these are the kinds of quantities that we want to collect. We're going to come back to this in much more detail momentarily, but just wanted to have people have that in their heads for now. Okay, so let's erase all of this. Come on, can I not do that? There's nothing I can do. Okay, that'll just have to sit here. So what do these quantities look like in practice? Like we said, P of y is going to be a table that's a distribution over all the labels I might see, and P of, say, f3, this pixel here, being on, given that I saw y, is going to be a table of probabilities that looks like this. For every value of y, what's the probability that that pixel is on? What does this whole table add up to? Who knows, right? Because this is just sort of a free thing on the right side of the conditioning bar and a fixed thing on the left side of the conditioning bar. When we talk about these kinds of naive Bayes models for text, we usually talk about a slightly different class of model that says, where basically we're going to start by defining a distribution over the whole vocabulary of words that we might see. And then the probability of a document is for each word that appears in that document, what's the probability that I saw that word anywhere, given the class of the document. And so the kind of sampling process underneath this that we can imagine is I first choose whether I'm going to send a spam email or a ham email, and then I have a particular distribution over the vocabulary associated with spam emails that maybe puts a lot more mass on dollar values and things in all caps and trying to sell you machines that will make parts of your body bigger. And I'm just going to sample from that distribution over and over again, you know, and that's where we imagine our document coming from. These kinds of models for text are sometimes called bag of words models. And the reason they're called bag of words models is because they don't care about the ordering, right? This product, which is a product over all the words that occur in the document, the ordering doesn't matter because it's just for each word, what was the probability that I saw that word anywhere given the label for this document. So you could permute all of the words in the document, totally shuffle everything, and we would assign exactly the same probability to a label after that permutation. So this is why, you know, again, we call these things naive Bayes models in general because this is a ridiculous independent assumption that words are independent of each other. But it works. Questions? Okay, and so to come back to the spam filtering example one more time, what are our parameter tables going to look like? They're going to look like this. First of all, for P of y, what do we think about for P of w given spam? So that is to say, what is, you know, this is a distribution over all the words in the language. What is the most probable word to see in a spam email? Okay, so we have people saying free. We have people saying buy. What else might be the most, given that remember, think about the question carefully. Given that this is a spam email, what word are you most likely to see in this spam email? Not spam. Okay. What about the? But that's not the question, right? The question is, given that this is a spam email, is it more probable that I saw the word the or that I saw the word free? The, right? So yeah, this I've now sort of totally written on top of this table and have to do a bunch of erasing. But yeah, so this is a really important distinction. Even though the is maybe, well, yeah. Even though this is a spam email, and the things that are going to allow us to distinguish it as a spam email from other kinds of emails are words like free and buy and $1 million. The most common word to see in a spam email is the. And the second most common word to see in a spam email is to. All these boring words. Because even spam emails have to include these boring words. And in fact, every spam email, whether it's trying to sell you a lottery ticket or get you to rescue someone from a prison in Spain or whatever, is going to have to use words like the and to and of. So, in a ham email, what's the most probable word? The, right? And to and of. This 2002 is kind of interesting. I guess the corpus this was collected from was in 2002, and so when people are replying to your emails, you know, it says on such and such a date in 2002, Jacob said this, and I think this is where this 2002 comes from. Okay, so really important thing. What is going to determine the behavior of our models is not the sort of absolute magnitudes of these probabilities that show up in the tables, but rather, for a particular word, is it assigned a higher probability in the spam table or a higher probability in the ham table? We're going to look at an example of this in a minute. The first thing is kind of a technical note. When I compute this, I have to compute this joint probability in order to query my model. I form this joint probability by multiplying together a bunch of things, right? P of y is some kind of probability. It's less than 1. This product here is going to range over a lot of words. Maybe my email has 500,000 words in it. And I'm multiplying together a bunch of probabilities that look like this, and each of these probabilities is small, right? Like the biggest probability I saw was about 0.1, and most of the probabilities of words are going to be much smaller than that. So what's going to happen to this, my estimate of this joint probability here? Yeah. It's going to be near to 0. It's going to be really tiny, because I've taken a bunch of numbers that are close to 0, and I've multiplied them all together. And in kind of real applications of this, it's not uncommon for you to actually get underflows and have your computer just round down to 0, and then you're doomed, right? Because you've forgotten everything you knew about the email. What we do instead is we work in log space. So we compute the log of the probability of everything jointly, and you'll remember that the log has this beautiful property that the log of P of y and then this product of whatever is equal to a sum of logarithms. So it's sum of log, well, it's like log P of y plus sum of log P of wi given y. These two things are equal. And so what that means is that we've gone from multiplying together a bunch of tiny numbers to adding together a bunch of kind of medium-sized negative numbers. And so this is going to have much better numerical behavior, and this is the way we actually implement these things in practice, and you're going to see that. So to do a concrete example of spam filtering now, we have something that looks like this. Before we have started reading any of the words in this email, we have a prior that tells us the probability of, well, you kind of ignore these column headings for now, but a priori we expect this email, 1/3 probability is spam, 2/3 probability ham. And these numbers that we've written in the total columns over here, this is just log of 0.3 and this is log of 0.6. I see the first word in my email. The first word is Gary. Gary occurs with very low probability under the ham distribution, but it occurs with even lower probability under the spam distribution. And so when I update my kind of running probabilities here, and these correspond to that big sum that we had on the previous slide, I am less confident that this is a spam email than I am that it is a ham email. And so the spam number goes down a lot, the ham number goes down less. The next word I see is wood. Wood is more likely to be associated with ham than spam, so the same thing happens. Next word is you. You is more likely to be associated with spam than ham. So the sort of change in spam is smaller than the change in the ham number over here, but we've still seen enough evidence for ham that we still think this email is going to be ham overall. But we're going to read the rest of this email, and it's going to say, Gary, would you like to lose weight while you sleep? This is clearly a spam email, and in fact, what we conclude at the end of the day is that this number that we've associated for spam is sort of a bigger number, remember, because this is a log, a bigger number than the number that we've associated with ham. And so in particular, if I go in and I compute the probability of spam given all the evidence, or ham given all the evidence, I find that it's 98.9% in favor of spam, and only like whatever the difference is, 1.1% in favor of ham. Where did this 98.9 come from? Well, we take these two, remember, this is the log of the joint probability of all the evidence and spam. This is the log of the joint probability of all the evidence and ham. And so like we always do with Bayes nets, we normalize these. And so this 98.9 is e to the negative 76 over e to the negative 76 plus e to the negative 80. People see where this comes from. Okay. So we've talked about the general problem that we're trying to solve. We talked about what these models look like once we've actually acquired them. What we're going to talk about in the next portion of this lecture is the kind of procedure that we go through in the course of actually training models. In particular, right, we saw at the very beginning that kind of the things that we need to set up one of these machine learning problems is we need to set up a data set, a collection of examples labeled with the particular classification decisions we want to make for them, and we need to define features for our problem that are going to allow us to turn these examples, these data, into things that the computer can assume. What we're next going to do is we're going to take that data set that we produced, and we're going to chop it up into three pieces, into a training set, a held out set, which you'll sometimes hear called a development set or a validation set, and finally a test set that looks like this. And our experimental cycle is going to go as follows. We're going to use each of these splits of the data set that we created for different purposes. We're going to use the training set to directly estimate the parameters of the model, so to do this counting procedure like we were looking at a couple of slides back. We're going to use the held out set to sort of validate that our model is doing reasonable things. So the sort of computer, the machine learning process is using the training data. You, the human, are using the held out data to figure out whether or not the machine learning is doing the right thing, right? So you're going to take this model you've learned on the training data, you're going to apply it to some held out data, and you're going to use what happens on the held out data to drive your model making decisions, right? So, maybe I train it and I find that my performance is not as good as I wanted it to be on the held out data set, and this could be because my features are bad or because I chose the wrong Bayes net structure or whatever. And so you, the human designer, are using this held out data in a kind of outer loop to figure out how to design the model. And then this test set, you never ever look at, and you run on it exactly once when it is time for you to take your model and present it to the world and try to persuade everyone else that your model has done a good thing. Why do we do this? Yeah?
If you don't separate out the test data, you might just be conforming your model to that test data.
Exactly, right. So it could be that I've defined a really weird set of features that work very well on my test data or on my training data and don't work well on any other randomly sampled data set. It might be and it might even be the case that if I kind of go back and forth enough between the training data and the held out data, I fit the training data really well, I fit the held out data really well, but when I come to some new data set that I've never had a chance to look at or evaluate on or anything before, my performance is terrible. This thing that happens where we get a model that works really well on one data set that we use to train it or to design it and doesn't work well in other places is called overfitting, and we're momentarily going to be sort of formalizing a little bit what we mean by overfitting. But the key thing to keep in your head here is that the way we avoid overfitting and the way in particular we avoid kind of advertising our models to other people as performing much better than they actually will in practice is by being very, very careful about maintaining the strict separation between the training set and the held out set and the test set. There's a big image classification challenge that gets run by I think some people at Stanford every year, and there was a big scandal 2 or 3 years back when the vision team at Baidu, the Chinese search company, was discovered to have gotten the best they won the this image recognition challenge that year. But the way they did it is they created 10 fake accounts. And so there was a server for this challenge that you were only allowed to submit to like twice a year, and that would give you your results on the test set. And so what these people had done instead is they had created a bunch of fake accounts. This allowed them to hit the test server 10 times as often as everyone else. And so they were able to just kind of hill climb on which models were doing well without actually necessarily making progress in a way that would generalize to yet another held out set. So the point is that the reason we don't run on test sets very often is because it's easy to overfit, and ultimately we have to have some way of judging like an absolute measure of the quality of the models that we produce, and the best way we know how to do this is with this kind of split like we have here. Yeah.
What's the difference between the training and the
So the training data we're going to hand to our model, and our model is going to estimate parameters from it. It could be, it's easy to write down, and we're going to see an example of this in a minute. It's easy to write down models that do unbelievably well on the training set, right? In fact, here's a model that does really well on the training set. Every time you see a training example, you memorize what the label was for that training example. And if I ever see exactly that training example ever again, I predict the label that I saw for it. And if I see a training example I've never seen before, I guess randomly. This thing gets 100% accuracy on the training set. But it's useless. Yeah, and so the reason you have a validation set is so that you can notice if you've made a mistake like that your model's kind of doing too well on the training set in ways that don't generalize, and for you to be able to fix that problem before you have to take it out into the world and use it in practice. Yeah.
So before we use the validation set, we can now do the test there, right?
Yeah, you should. I mean, again, just as a kind of methodological thing, you run on the test set once. You run on it, before you're going to take your thing into the meeting with the CEO or before you're going to publish your paper, and never before, because it's supposed to be, this is our best way of getting an accurate measurement of how well the thing actually does. We've spent a lot of time on this slide. I think it might be the most important slide in this class. You guys, some of you are going to go out into the world. You're going to be working in industry. You're going to be working as researchers or engineers on kind of real products that use artificial intelligence. You're going to be building, medical diagnosis systems and like algorithmic trading systems and self-driving cars. And if you do this wrong, bad things are going to happen. If you advertise to other people that your model does better than it actually will, then if you say it's going to generalize in ways that it won't generalize, people will die. Cars will crash. People will lose their savings. People will take the wrong drugs. So, data hygiene is serious business, and that's all I have to say about this. Okay, so let's talk about what it actually means to overfit. Sorry, that got very dark very quickly, but it's true. How many people have not seen, let's say, regression of any kind before? Okay, so everyone knows what we're trying to do here. I have a bunch of points, and I want to find some kind of function that fits these points, right? So I have my x and my y, and when somebody brings me a new x, I want to predict what the y associated with it is. This is the same kind of problem that we were trying to solve before, but now with real valued quantities rather than discrete decisions. What is a function that I might use to fit this set of dots that I have here? Or like a class of functions? Yeah. Sorry? Polynomials, okay. There are many different kinds of polynomials. Let's choose a first order polynomial, right? So a straight line. So I look at this data set and I say, give me the straight line that is as close as possible to all of these data points, and it looks something like this. Okay, this is maybe good, but we can probably do better, right? You had suggested a quadratic originally. If I instead, okay, so remember, this is a model of the form y equals mx plus b. Maybe we could fit a second order model of this instead, and that'll look probably something like this. And this is, remember, a model of the form y equals ax squared plus bx plus c. And we're choosing, in the first case, we're picking m and b based on the data. In the second case, we're choosing a and b and c based on the data. Okay, these things all like do a reasonably good job of fitting the set of points that I have here. Can we do even better at fitting these points? Let's just add more. Okay, somebody's sitting in the back going like this, and sure enough, let's fit a degree 15 polynomial to this set of points. It looks like this. And it does really well, right? It gets really close to all of my data points here. What has gone wrong? Yeah.
If you were to actually fill in all the points in between, it would look nothing like that.
Probably, right? Like, you know, it might turn out that in fact these are the only x values that you can ever observe, and this is really great because it gets the right answer for all of these x values and you don't care what's happening anywhere else. But, you know, probably under our kind of like reasonable model of what the world looks like, there's going to be an x value here, there's going to be an x value here, and, you know, it would be a very weird process that I'm trying to fit indeed if it jumped from being 0 here to being 25 here and then right back down to 0, this function that I'm trying to fit, right? So by doing really well, by doing as well as possible on this training set, I have created a model that is doing crazy things in the region of x space that I didn't get to see at training time. And it's probably not going to be a good model. And this is the kind of thing that we want to discover by running on our validation set. And when we find this, when we find that there's a huge difference in performance between what we get on the training set and what we get on the validation set, we call this overfitting. Here's another example of overfitting. This is coming back to this digit recognition task. So say we have the following image here, and we want to know whether it's a 2 or a 3. And so our probabilities look like this, you know, for some like fixed pixel that we're looking at. Yeah, so you know, we have a prior over classes that's uniform. For this particular pixel, the probability that it's on, if it's a 2 is 0.8, same if it's a 0.3, so this doesn't tell us anything one way or the other. But looking at this point, you know, we're much more sure that it belongs to a 3 than a 2. Looking at this point, we're much more sure that it belongs to a 3 than a 2. And then we come to this point down here. And suppose it was the case that in our training set, we, you know, this is like sensor noise. This is something's gone wrong with our camera, or there was a speck of dust on the page when I was taking a picture of it or something. You know, it's random chance that we saw this, and we rarely see it. We see it only 1% of the time in 2s, and it turns out in the training set that we had that we never saw it with 3s. What's the probability that our model is going to assign to this thing being a 3? 0. Why? Because I'm just multiplying all of these probabilities together, and as soon as there's a 0 there, it can wipe everything else out. So as soon as I say this pixel is impossible, if the true class is a 3, then there is no longer any chance that it can be a 3, no matter how small that probability is that we assign to a 2. And right, more generally, we said before that the quantities that we care about are the kind of relative ratios of the individual features we see given the two classes. And if there's ever a feature that only shows up in one class and not in the other class, then when we compute these tables of ratios, it's going to be full of infinities, and it's going to totally break our calculation. It's going to wipe out whatever probability we might have assigned to the other class, no matter how strong the other evidence that we have for that class is. So the point is that if I just take these relative frequency parameters, if there are very low frequency events, those will almost always cause me to overfit. Sorry, the fact that I never saw this particular location in any 3 at training time doesn't in general mean that I'm never going to see it at test time. And the issue here is just that this was such a low outcome event, this pixel being on in the corner a priori, that I never got to see very many examples of it. Maybe if I had kind of an infinitely large data set, then I would have been able to do the right thing with it. But in practice, all of the data sets that we ever have are data sets of finite size. And so this is a way we're going to get into trouble. And this kind of comes back to the example we were doing before, where I define a feature that's just like, is this identical to one of my training examples or not? This is a great feature, but it won't generalize at all. It will always overfit. So there are 2 ways we can get around this. We can get around this by defining features that are sort of general features and won't memorize too much about individual training examples. But the point of this previous slide that we were looking at, or sorry, yeah, the slide with the 3, was that just having simple features is sometimes not enough, because even infrequent simple features will sometimes get you into trouble. And so we also need some way of improving our estimates of the parameter values as well. And this is called smoothing. So let's start by reminding ourselves of where these parameter estimates were coming from in the first place. And so we said we can either elicit these from people or we can use training data. And the way that we've learned to use training data is for each of the outcomes that we care about, we just count the number of times that outcome occurs relative to everything else that happens in the world. Why is this a reasonable thing to do? Like, what's magical about this particular estimate for a probability distribution that I'm trying to fit? Oh, sorry, I just gave it away. What's magical about it? Yeah.
Is it because it's trying to represent, like, or from given as much knowledge as we have, it's trying to represent what bigger samples or the bigger spaces, like distribution of the bigger space?
Not sure I understand.
I'm not sure.
Okay. Yeah.
Is it because based on the evidence so far, it's our best estimate for the actual probability of that sample?
Yeah, and maybe this is what you were trying to say before. So if you remember when we were doing sampling, there was a quantity that we could compute about a sample that we called the likelihood of that sample. It turns out, and it's not at all obvious just by inspecting this when we have it written up on the screen here, that in a BaseNet, if you want to assign the highest possible probability that the BaseNet will allow you to all of the sort of examples, to all of the data points that you've seen from the world, the way to do that is by this counting procedure. Ooh, going back. Sorry. Yeah. So if I want to find a theta, if I want to fill in all of the probability tables in my BaseNet in a way that maximizes the probability that my BaseNet assigns to all of my data, the way you do that is with this counting procedure. We will look at ways of proving that later, I think, but for now, kind of take it as a given that this is a fact that is true. And so we call this the maximum likelihood estimator because it is the estimator that maximizes the likelihood of my data of all of the sort of values that I could choose for theta for my fixed model structure. Yeah, so this is what maximum likelihood estimation looks like. And we saw before that maximum likelihood estimation is going to get us into trouble for these very low frequency events. Another thing that we can try to do instead is what's called maximum a posteriori estimation, usually just MAP. And what that says is rather than trying to maximize the probability of the data given my parameters, I want to maximize the probability of my parameters given the data. What does that mean? Well, I don't really know, but I can apply Bayes' rule here. And Bayes' rule tells me that whatever this thing is, it's definitely equal to this quantity down below, which is just the likelihood times some p of theta, and then divided by some quantity that only depends on x and doesn't depend on theta and is not going to affect our optimization at all. And so by saying let's maximize the probability of the parameters rather than the probability of the data or the likelihood of the data, what this turns into is just maximizing a scaled version of the likelihood of the data times some prior that you place on what the parameters look like themselves. And this suddenly gives us a handle on preventing the kind of behavior that we saw before. If we never want any of the entries in these probability tables to go to 0, then we can choose this p of theta to place very, very, very low probability, or maybe no probability at all, on the entry on scenarios where the entries in those tables wind up being set to 0. It turns out that when we do this kind of map estimation, it doesn't always have a sort of beautiful, clean form like we saw with maximum likelihood. And so what we're going to be looking at instead for the rest of today in the couple of minutes that we have left is sort of concrete examples of these things, of procedures that we can use for estimating these things other than just directly counting. And these are all going to happen to correspond to multiplying by priors over theta, but we're not going to be talking about that in this class. And if you're really interested in this stuff, take other machine learning classes at Berkeley. Questions about what we've done here, why we would want to do this, why we'd want to do this, and what the two differences are between them. Okay. So let's make this a little bit more concrete. What we said is that we want to kind of avoid freaking out when things that we haven't accounted for happen. So here's a very, very old problem that goes back to Laplace, who was a French mathematician in like the 18th or 17th century, who wanted to know what the probability was that the sun was going to rise tomorrow. Let's make this slightly more concrete, and let's say you're trying to estimate the probability that the sun is going to rise at 8 p.m. or at 8 a.m. rather tomorrow morning. So you wake up today, and you see the sun rise, and the sun rises at 8 a.m. So you say, okay, I've seen one outcome, and that outcome was that the sun rose at 8 a.m. So on 100% of days, the sun will rise at 8 a.m. I place all of my probability mass on the sun rising at 8 a.m. and none of my probability mass on the sun rising at any other time. And then tomorrow comes, and 8 a.m. comes and goes, and the sun hasn't risen yet. And it turns out the sun was going to come up at 8:01 instead. But we totally freaked out because we said, with 100% probability, certainly the sun was going to rise at 8 a.m., so the world must have ended. And so the issue here was that we put all of our mass on one outcome, and so we were totally unprepared to deal with anything else that might have happened. And the way Laplace gets around this problem, and the sort of technique that we derive from that, that's called Laplace smoothing, is you just pretend that you saw every outcome that might have happened once more than you actually did. So rather than saying, starting on before you've seen anything and saying, kind of day 0, I've never seen the sun rise. Day 1, I've seen the sun rise exactly once and it rose at 8 a.m. What you say is, well, on day 0, I've seen the sun rise once at every possible time the sun might have risen. And then when I see the sun rise at 8 a.m., you say, okay, well now I have slightly more evidence for the sun rising at 8 a.m., but I still think there's some possibility that it might rise at all of the other times instead. Yeah?
But doesn't that force you to create a lot of unnecessary data sometimes?
Well, it depends on what you mean by unnecessary data. I mean, right, we're going to have to fill in this table of probabilities for when the sun is going to rise anyway. This is a thing that we have to represent. And the data structure that contains all of our counts is the same size as this. So if we just start by populating the table of counts with 1s, and then when the sun rises at 8, we increment this count, and we say this is 2, we haven't really wasted any space. Does that make sense? Okay. So, like we said before, it turns out there is a particular thing you can choose for P of theta that will justify this in beautiful theoretical terms. And if you're interested in that, take CS281A. But yeah, so for example, in this red, red, blue counting thing that we were doing before, what's the maximum likelihood estimate for the probability of red? Two-thirds, right? And so for blue, correspondingly, it's 1/3. What's the maximum likelihood estimate? Or sorry, what's the Laplace estimate for the probability of red? Okay, so somebody said 3/4. 3/5. Okay, who thinks it's 3/4? Who thinks it's 3/5? Okay, why 3/5? Somebody who just raised their hand. Yeah.
You have to add one sample for red and also blue.
Right, you have to add one sample for red and one sample for blue. So we're imagining that basically I've added another red ball here, and I've also added another blue ball here. So now there are 5 balls, 3 of them are red, 2 of them are blue, and sure enough, the Laplace estimate that we get in this case is 3/5. We can do a kind of more general version of this depending on how conservative we want to be, and we can pretend that we've seen many, many more of these samples. So, for example, I can do Laplace smoothing, So if I do Laplace smoothing with k equals 0 with no smoothing, then I'm back to my maximum likelihood estimate like we saw before. We can do it with 1, and we got what we saw here. And the bigger I make this k parameter, the harder and harder it's going to be for me to move away from a uniform distribution. So what you can kind of think of this procedure doing in interpretable terms is saying basically the higher k is, the more I think ahead of time The true distribution of my parameters should be uniform, and the more evidence it's going to take to convince me that it's something other than the uniform distribution. And right, obviously in the limit where k goes to infinity, no amount of evidence will ever persuade me to revise that initial estimate. Okay, yeah, and remember that kind of we're going to do a similar trick with conditionals, and you just have to be careful about all of your bookkeeping when you fill in the tables. You're going to spend a lot of time in this in discussion section, so don't worry about these details. Yeah, so as it turns out, Laplace smoothing is kind of a stupid thing to do for real-world applications. It doesn't give you great performance when the set of outcomes is very large, or when the set of labels is very large, because it kind of has this weird property of forcing you to be super conservative some of the time. And so there are various other smoothing techniques that we can use instead. You can kind of start with the empirical estimate of p of x, so ignore all of the labels, and just say what fraction of the time, in any training example, do I ever see this feature turned on, and smoothly interpolate between your sort of maximum likelihood estimate of that and the thing that you get when you ignore the labels. This is a huge area of research. People write whole PhD dissertations on it. The math is really pretty, and I encourage you all to take other classes later on talking about these things. So coming back to this naive Bayes example that we were looking at before, if we do any kind of smoothing procedure, suddenly, right, there's no way for me to wind up with infinities in these tables of odds ratios, because I've always seen this outcome at least once, and I've always seen this outcome at least once. I've always seen this outcome at least once, and so on. And so this is a way of avoiding these kinds of singularities, and basically when features get turned on very infrequently, we don't expect them to provide us much information one way or another, and this is a way of kind of quantifying that. And here's another picture. Okay. How much time do we have left? Let's see how far we can get. Okay, so what we've talked about now is how to estimate these parameters. But what we've found is that we actually now have two different kinds of parameters in our model, right? We have the actual entries in the tables that are getting estimated by our machine learning procedure, just this counting thing that we're talking about. And now we also have sort of what are called hyperparameters, which are how big should I make k, how conservative should I be about filling in these tables, or in this linear thing, how much should I interpolate between the distribution I saw and the distribution that I would have had ahead of time. These hyperparameters are not, basically to first order are not things that we can estimate in the same way that we can estimate the real model parameters, right? It doesn't make sense to choose the hyperparameter that maximizes the likelihood of the data you've seen, because that's always going to be the hyperparameter that kind of makes the distribution you're trying to fit as close as possible to the true maximum likelihood distribution. So the hyperparameters we can only really choose on the basis of this held out data rather than the data that we're actually learning our model from. And so this is why having a held out set becomes really important. Because what we're going to do is we're going to pick a hyperparameter, we're going to go to the training set, we're going to train our model, we'll run it on the held out set and see how well it does there. And depending on how well it does in the held out set, maybe we adjust our hyperparameters, or maybe we're happy with the performance that we're getting. And so this is what this experimental process looks like, is that we're going back and forth between learning the model on the training set and fitting hyperparameters, basically by hand ourselves on the held out set. Is it clear to people why we don't want to learn hyperparameters? Why do we don't want to choose hyperparameters on the basis of the training set? Okay. Great. So, the only other thing that we have left on the menu today is talking about how to design features and how to deal with errors. And I don't think there's actually that much intuition we can provide here. It kind of depends on the problem that you're working on. But, basically, as a kind of diagnostic for figuring out why is my machine learning model not working, the most useful thing you can do, you run it on the validation set, you have it spit out a bunch of examples that it's misclassifying, and you kind of think to yourself, well, what would I need to do? What would I need to know differently about these two examples in order to discriminate among them, or to be able to assign them the right labels without breaking everything else? You can always make your accuracy on the training set go up by adding more features, and sometimes that will also help you on the validation set if you're underfit, and sometimes that will hurt you on the validation set if it causes you to overfit. And yeah, that's basically it. So I mean, we can talk a little bit more about experimental hygiene and how to design these things, but this is a whole big topic that I don't really want to start right now. So let's just wrap it up for today. Questions before we finish? Okay, great. Good luck on the exam tomorrow, everyone.